So, happy Monday. Yay. Happy cooler weather. Yeah, we can actually use the second half of your closet, at least in the morning, till about 10. So, today we're continuing on with the atomic orbital information, but today's a very important day, so I'm glad you're here. We're going to be reviewing electron configurations, but we're also going to be going deeper into electron configurations than you ever went before. So, do you remember the 1s2, 2s2, yeah, all of that stuff? Don't be bored, because we're going to dive into where the data comes from that supports all of the trends that we talked about. So we're going to really dive into electron configurations. You can't understand atomic spectroscopy without understanding electron configurations, because all of the peaks in the spectrum come from different electron configurations. And so you've got to understand where the electrons are and what they're doing in terms of the configuration before you can understand when they jump between configurations, because that's what's happening in spectroscopy. We jump between different levels. Let's jump in. Okay, so this, picking up where we left off, was the hydrogenic energy levels. And we said that in the hydrogenic system, with just one electron, there was no energy dependence upon angular momentum. In English, that means there's no energy difference between a 2s and a 2p orbital, because the only difference is the angular momentum, the s and the p. It's still, the in principal quantum number n is still 2 in that situation. But that's only the case in the hydrogenic energy equation. When you go to multi-electron orbitals and energy levels, then you have a term that increases the energy when you go from an s to a p. And that makes sense logically if you think about it. You've got an increase in nodes, you should have an increase in energy, right? If you're going up from an s, which is a spherical orbital with no planar nodes, and you go to a p, now you have more curvature, you should have more kinetic energy in that orbital. And so we see that in multi-electron orbitals and energy levels. And so you can see from this 2p in the multi-electron atom, that 2p has moved up, and now it's a higher energy than the 2s. And so this is where we get all of our electron configurations and the order in which those electrons go. Now, naturally, if you've got a nucleus and you drop an electron onto a bare nucleus, it's going to go all the way as close to that nucleus as it can get. And that 1s orbital would be the first one that it can fill. And that's the closest to the nucleus. But once it's full, and the Pauli exclusion principle won't let you put a third electron into the 1s orbital, it goes into the 2p orbital. It's not going to stay in the 2s orbital. It's not going to stay in the 2p, because that's not as close to the nucleus as the 2s. So the electrons fall down as close as they can to that positive charge in the nucleus. Make sense? Okay. So then, as we look at these orbitals, the 2s, the 2p, then the 3s is the next closest, then the 3p, then the 4s. But notice the 4s comes before the 3d. And so this is review. You should go back through your freshman notes, but basically this PowerPoint would cover the whole review. Is this strange order: 1s, 2s, 2p, 3s, 3p, and then 4s before the 3d, and then 4p before the 5s. And so instead of having to remember this whole complex energy level diagram, you can use this little scheme here. So many of you have used this, where you just write out all of the orbitals. Notice how if you write it out this way, the different rows are the different shells. Okay, so these are some terms that we need to have in our minds. So when I say shell, you know I'm talking about principal quantum number. So everything with a principal quantum number 3 is in the same shell. Okay, so then what do we call S, P, and D? Those are subshells. So shells versus subshells, important distinction. Later on, when we're talking about trends, there is no trend to the half-filled shell, but there is a trend with the half-filled subshell. So you see that word sub is important. Okay. And so this is the simple way to remember that filling scheme. It's kind of surprising. It's just sort of a text-based mnemonic, but it does match the energy level spacing. So it's really nothing to do with this little trick. It has everything to do with the relative energy levels of those orbitals, but this does match the ordering in the periodic table. So if you're coming along, you have hydrogen, helium, that's 1s, then 2s for lithium and beryllium, then 2p for boron through neon, then 3s for sodium, 3p for aluminum, and then you don't go to the 3d, you go to the 4s at potassium. And it's nice to see on the periodic table there's a 4 right there. So you can just jump down here and know that that's the first electron in the 4 shell. That's 4s. 4s1, 4s2. But the thing you have to remember is that the 3d has dropped down. And this is 3d, 1 through 10. And then back to 4p. So the 3d orbitals are on the 4th row of the periodic table. And that you get that from this little scheme here. So if you can tie this to the periodic table, and you always have a periodic table with you, like I've got one in my wallet, believe me, I've got it right here. Okay, then you can always know your electron configurations. Okay, so you really don't need to memorize that. If you can relate it to the periodic table, you're golden. Okay. Now, one of the trends that we will develop later, she's like, I don't believe this. But anyway, one of the trends we'll talk about later is that half-filled subshells are energetically favored. Now, what does that mean, energetically favored? Well, you could write out chromium. If you look at the periodic table, it's over here at D4, right? 3D4. Well, we have a 4S1 and 2 here and a 3D4. It's one away from a D5, which is half-filled subshell. So it will steal an electron from the 4S, and now we have a half-filled 4S and a half-filled 3D subshell, and the whole atom drops in energy. Okay? It's not just about the orbital energies, it's about the energy of the whole atom. So you can make a chromium like this, but that particular atom is a little bit higher in energy. And so when that electron oscillates and jumps over to the D subshell, then the whole atom relaxes a little bit. And so we're really talking about the energy of the whole atom, not just static energies of these different orbitals. So before we get into electron configurations, let's reach back a little bit. We talked about the 4 quantum numbers, N, L, M sub L, and M sub S. And I want you to think about in these particular electron configurations, we need to identify any unfilled subshells. We need to identify the quantum numbers, especially the angular momentum quantum number for that last electron, because that's going to be important for our term symbols. So this is just a little bit of practice. Let's do a few of these. So what are L, S, and the multiplicity for the following atoms? So for hydrogen, we just have a 1s1. And so that last electron has L equals what? 0, exactly. So L is equal to 0. And then the spin of the whole atom, is just taking as if all of those unpaired electrons are plus 1/2. And so you add up all of the electrons that are unpaired, and you see what S is. So S is equal to what? So the spin of this atom with this unpaired electron in an s orbital, what's the spin of that unpaired electron? So M sub S is the spin, so plus 1/2. So S is plus 1/2. Okay, and then the multiplicity, which there's not a letter. We've defined letters for everything in this whole course except for the multiplicity. That is 2s plus 1. So we have to find S before we can do the multiplicity. And so once we have S as 1/2, we have 2 times 1/2 plus 1. So that 2 times 1/2 is 1 plus 1. That's equal to 2. So 2, and we call that a doublet. So this is an exercise that you're going to have to just be like that for. And so let's go to, let's see, let's do boron. That'll be interesting. So we'll skip lithium and go to boron. What's the electron configuration for boron? Well, it has 1s2, 2s2, 2p1. You can look at the periodic table, follow along. It goes past helium, so that's 1s2. Goes past beryllium, that's 2s2, and it's the first one in the p block, so it's 2p1. What's the angular momentum quantum number for this atom, for the whole atom? Okay. Once you have a filled subshell, then that angular momentum is sort of canceled out. You've got an electron essentially going this way and one going the opposite direction. You could think of it that way. So when that shell is filled, all of the angular momentum cancel, and you're only looking at unfilled subshells. So in determining all of these, you're only looking at unfilled subshells. Important concept. Okay? When we get to term symbols, you're only looking at the unfilled subshells. So you don't have to worry about everything that's below the 2p1 in this example. So we just have to look at that last electron, and it's in a p orbital. So what is L? Yes, L equals 1. Because S is equal to 0, P is equal to 1, D is equal to 2, F is equal to 3. And that's pretty much as far as you have to go. So SPDF, 0, 1, 2, 3. Okay. And then again, it's a single electron. We assume it's spin up. So that's plus 1/2. And so then the multiplicity is a doublet again. 2 times 1/2 is equal to 2. So the multiplicity is 2. Now what's interesting about this is in terms of how we developed this theory, it was really backwards. We noticed that the spectrum had 2 peaks in it, and we called it a doublet. And we didn't know why. Well, it was because the absorption was split by the spin up and spin down electron. If you just had one unpaired electron, you had a doublet. And so that's where this name came from, but it's sort of backwards the way we develop it. So it's going to exhibit a doublet in the spectrum. So that's where that word comes from, two peaks closely spaced. But in terms of supporting why it's a doublet, we've got to go all the way back to the electron configuration. Let's look at this one here, helium with 1s1, 2s1. So you can have excited state configurations. So we've taken an electron that should have been the 1s2 electron and put it into the 2s. And so this is something that may be new to you. We've got electron configurations, but most of the time we think of them as ground state electron configurations, but they can have all kinds of other configurations. So helium, you can put that electron in the 2s, and now you have options because they're in different orbitals. So you can have spin up, spin down, or you can have spin up, spin up. Because they're in different orbitals, one in the 2s, one in the 1s, they don't have a restriction on the same four, well, there's still a restriction on the same 4 quantum numbers, but because they're in different orbitals, they have a different principal quantum number. And so they can both be spin up now. So let's do the spin up, spin down case where they're still paired together. And let's look at this. Now because we have 2 unpaired electrons, 2 unfilled subshells, we've got to put 1s and 2s on our angular momentum quantum numbers. And so here we have L1 is equal to, for electron 1, 0 because it's an s orbital. L2 is equal to 0. So because both those electrons are in s orbitals, both of them have an angular momentum of 0. This is building up towards next lecture when we start looking at all of the combinations of electrons. And so then what's the spin for S1? S1 is equal to plus 1/2. Like I said, we'll assume that they're both spin up at this point. Or no, I said spin up and spin down. So let's put S2 as minus 1/2. And so S total, in this case, is equal to 0. Right, because you got a plus 1/2 and a minus 1/2. You add them together and you get 0. And so then in this case, the 2s plus 1 will be 2 times 0 plus 1. I've kind of got my parentheses screwed up here. Let's put a parenthesis around these 2's. Go back in your notes and look up here. It's 2s plus 1, not 2s plus 1. And this gives 1, and that's called a singlet. And so whenever we have paired electrons, Whenever we have paired electrons, we have a singlet. Okay. What about unpaired electrons? Let's come down here and let's say, what if we had S1 equals plus 1/2 and S2 equals plus 1/2? S total would equal 1, and 2 times 1 plus 1 would equal 3, and that's a triplet. Keep hitting that with my wrist. Okay. So this should be something that we will work on, but eventually this will be quick for you. It's just adding up the spins of an electron. If they're unpaired, they add together. 2 electrons gives you a plus 1 total spin, and then 2s plus 1 is 3. That's a triplet. Eventually, you can just look at this number. A triplet means there's 2 unpaired electrons. Okay. A doublet means there's 1 unpaired electron. A singlet means there's 0 unpaired electrons. Now, how is a singlet unpaired? Well, they're in different orbitals, but they're still paired, spin up, spin down. And so their spins still cancel for the whole atom. So this is just some practice on identifying the angular momentum and spin quantum numbers for the different electrons in an electron configuration. We're going to revisit this next time when we get to the Clebsch-Gordon series and looking at all the combinations of spin in a particular atom. So let's go back and now practice with electron configurations. And this is the data that gives us all of the trends in our electron configurations. So these are the first ionization energies. And this, like spectroscopy, is a difference between 2 levels. One energy level is a neutral atom, and one energy level is the cation. Okay. And so you have this E1, this ionization energy. You've got the energy level of the cation. And the energy level of the neutral. And so when you hit this with light, you're going to see an absorption related to that first ionization energy. And an electron's going to come out. Okay? You could detect that electron. That would be something like UV or X-ray photoelectron spectroscopy, but in this case it's the valence electron. It's the outermost electron, so that would be in the UV. So UV photoelectron spectroscopy, if you're looking at the electron, or if you're just looking at absorption, you'll see this peak, the very first peak where it starts to absorb in the atom. You're going to get this first ionization energy. And let's look at the trends. Can you, before we get to the next page of the notes, can you identify some trends in the data? What's that? I hear somebody moving. Go ahead.
It resets after each subshell.
Yeah, it resets. You see it kind of grows up and then there's a slam down. What's going on? If you notice, those highest peaks are the noble gases. Yeah, so when we reach the end of the periodic table, boom, there's this jump down. Now low, on this Y scale, that's easy to ionize. And so what is high? Hard to ionize, and you see the noble gases, right? Very non-reactive because they're stable. What we're saying about stable shells, we actually are saying that because of this data. Okay. We're not saying the data is the way it is because the shells are stable. We're saying the shells must be stable because of this data. You see, data first. Okay. So when we see that the noble gases are so hard to ionize, we conclude they must be stable. They must be stable to oxidative attack or anything like that that's going to take an electron from them. Okay. And then look at the bottom ones. Lithium, sodium, potassium, rubidium, cesium. First group, okay, the alkali metals. Again, those are easy to ionize. We don't take our memorized trend and say, aha, they're easy to ionize, therefore the data. No, the data shows they're easy to ionize, therefore those cations are very easy to lose their electrons, those alkali metals. And then the things in between. Why would the ionization energy increase so dramatically across a row in a periodic table? So let's think about what's happening when we go from, say, sodium to magnesium. Okay, so we've got a sodium atom. Let's build a magnesium atom. We stick another proton in the nucleus. We stick maybe another neutron in there too to stabilize the nucleus. And so now it's got one more plus charge. And we put an electron on there to make the neutral magnesium atom. Now, what kind of nucleus does that electron see? Is that all the previous protons completely shielded by all the previous electrons? And so that next electron only sees one more plus charge? The answer is no. Okay, so we have incomplete shielding of the nuclei by these electrons that we add on. So we add another proton, and now we're over to aluminum, and we add another electron. But that electron doesn't just see one more plus charge, it sees a lot of pluses. So it's pulled even closer. And when we add that extra proton, all the other previous electrons are pulled closer too. So as we add protons across a row in the periodic table, we're adding a lot of positive charge, and the electrons are not completely shielding that out, and so it's pulling that ball tighter and tighter and tighter. Okay. Until we get to a new principal quantum number, and those electrons are further out. Just because of their higher kinetic energy, they're stretched out more in space, and they see less of that nucleus. Okay. So it's more of a distance effect for the shells than it is the shielding effect. But going across a row in a periodic table, this data seems to suggest that there's incomplete shielding by the previous electrons, because you see it gets harder and harder to ionize. And then when we get to a new shell, then it's jumped out quite a bit in space. That's why I was saying it's important to understand that the electron on the hydrogen atom stretches down to spring, but the sodium atom, that electron's in Argentina, so it's a lot further away and a lot easier to ionize. So let's look at these trends based upon their electron configurations. So let's explain all of these trends. And these are 5 trends in this data. So the first one, the first ionization energy decreases with the size of the atom. And you can write these down now, or you just wait till you get the notes. They're all in there. The first ionization energy increases across a row in the periodic table. That's the one we just talked about, that incomplete shielding of the electrons. These are some of the wiggles you see in the data. You see these orange circles here identifying some funny business that's going on within a row. So some of that funny business is that it seems to be from the data that the first ionization energy is unusually high from a fully filled subshell. So whenever you get a fully filled subshell, you have an unusually high ionization energy, and then from a half-filled subshell, you have an unusually high first ionization energy. And then you have an unusually low when you go past that fully filled subshell or half-filled subshell. So you go one electron past one of these stable configurations, and it's easy to pull that electron back off. Okay. So let's walk through these by hand, looking at all the different trends. So I've repeated this data 5 times, and we'll look at all 5 trends using electron configurations. So this one says the first ionization energy decreases with the size of the atom. So let's just use the noble gases for this one, since they're the top of the peaks and easy to see. You see, as we get to larger and larger atoms, that first ionization energy decreases. Okay. And so what we're looking at is helium, the difference between the neutral, okay, helium, which is 1s2, and helium cation, so we need to look at the electron configurations of each one of those. This energy difference, the first ionization potential, is much bigger gap than the radon. So the cation up there. Let me erase that little smudge. Okay. And why is that? Well, if you looked at those hydrogenic energy levels, and then with the adjustment for multi-electron atoms, did you notice how all of them got closer and closer together as you got higher in the principal quantum number and higher in the angular momentum quantum number? Okay, and so this is the difference between radon and radon cation. very small difference that far away from the nucleus. But close to the nucleus, very big difference for hydrogen, or helium, I should say, helium going from 1s2 to 1s1. So that makes sense. As the atom gets bigger, the energy levels of those different shells gets closer and closer together. Okay. What about this one? The first ionization energy increases across a row in the periodic table. So we saw this as well. So let's look at lithium cation, lithium neutral. Let's go ahead. Well, we're going to have to do the whole thing. 1s2, yeah. 1s2, 2s, and 1s2, that's it. So it's just losing that 2s electron. And that's a pretty big gap in lithium. Then we get over here to neon, and the neutral is really stabilized. 1s2, 2s2, 2p6. And so this is neon plus. And notice that the neutral, because it's got this really stable noble gas configuration, this level has dropped dramatically. The cation has dropped as well, but the neutral has really dropped. And so if that neutral has dropped so far, because again, those electrons are pulled closer to a nucleus because of inadequate shielding, then we've got a huge difference in the ionization potential. And so what we're thinking about is whether the neutral is stabilized or whether the cation is stabilized. And so this will become clear in the next couple of trends, thinking about whether the neutral has a stable configuration or the cation has a stable configuration. In this case, the neutral atom, neon, has that noble gas configuration. It's as low as it can go. Every electron has its own view of the nucleus, and we've got this super stable configuration where all of the quantum numbers are used up. So let's look at this now. Fully filled subshell. When I say unusually high, let's look at this row here, sodium through argon. If I were to just draw a line straight up through here, and the trend, I know it's kind of hard to see, but if the trend, let's see if I can do the zoom lens here. Oh, let's see, keep that. And let's get this guy. Yeah, okay, that's going to work. Okay, so look where the trend, if I just took the average ionization energy between all of those, you'd see it would go right between those 2 points. But those points, one point is high, the other point is low. And so this one here, I'll have to do this on the screen. This one here is unusually high. This is where I would predict it to be, right about there, but it's unusually high. And the next one is unusually low. I would predict it to be right here, but it's down too far. So we're going to look at these two trends. We see this, I've circled all of them in orange. Why is this one unusually high? That's what this trend is that we're talking about right now. So it looks like the first ionization energy is unusually high from fully filled subshells. So what's the subshell that's fully filled in the second atom over from lithium? That's beryllium. It's the 2s. The 2s is fully filled. Okay. So what we're saying is that the predicted trend, see if I can do this with the pen too. Okay, it won't let me do the pen with the zoom. So let me kill that. Okay, so I'll say predicted would be this difference for beryllium. And so this is the 1s2, 2s2, and 1s2, 2s. So just a single electron in the 2s. That's the cation. And it says this is unusually high, so it means that the difference is bigger. So it's bigger than what you would expect, the difference between these energy levels. So which one of these energy levels do you think moved? Which one is more stable, has a more stable electron configuration? The one that's fully filled. So that neutral has been stabilized a little bit and has dropped. This data seems to suggest, that's why I keep trying to use that word, the data seems to suggest that fully filled subshells are lower in energy than you would predict. What does that mean? That means this level has dropped a little bit because of this stable configuration. And if this level drops here, then the difference is bigger than you would expect. Get that? Okay, that's where we get this claim that fully filled subshells are stable. It's actually from this unusually high electron configuration, first ionization potential. Okay, so let's look at the next one, and this confirms the same claim. So the next one is that the first ionization energy. Let's see. Let's go back. I skipped. Where's the half filled? Okay, it's actually the fifth trend. Let's look at. Okay, so I insert nitrogen in between this. Okay, so there's also another trend here where nitrogen is unusually high. Okay, so this nitrogen is also unusually high. Do you see how it goes up and the oxygen drops down? So let's write out oxygen. So the nitrogen one. So nitrogen plus and nitrogen. So nitrogen is 1s2, 2s2, 2p3. And nitrogen cation, you just take one of those electrons away. 1s2, 2s2, 2p2. And I look at the data and I see that the nitrogen first ionization potential is unusually high. It's off the trend to the high side. And so which one of these would have moved? If I move the top one down, the energy level spacing gets smaller. And so that would be unusually low. So I have to move the bottom one down. If I move the bottom one down, then I get an unusually high ionization potential. And we see this half-filled subshell over here. The data seems to suggest that this energy level is lower than we would predict. Therefore, the difference is bigger. And so that's where we get the claim from the data that half-filled subshells are stable because they're dropping energy a little bit, and nitrogen has a higher ionization potential than it would have been predicted. Okay. So these claims, half-filled subshells are stable, fully filled subshells are stable, they come from this ionization data. And we can understand them only if we know how to do electron configurations. Let's look at this last one, where if we go past a half-filled subshell, or if we go past a fully filled subshell, it's unusually easy to ionize that atom. We see that with the sodium series, right? We go past the noble gas, it's really easy to ionize. But we also see in this trend boron. We see boron here, and we see oxygen. So let's look at boron. And boron cation. And I think, you're starting to figure out, okay, we can do electron configurations for cations too. And, you just, however many electrons you have, you just build it up using the same scheme. So boron, we have 1s2, 2s2, 2p1. And then up here, the cation, we have 1s2, 2s2. So we've lost that p electron. And this is unusually easy to ionize. So which one of these do you think moved? Which one of these energy levels? The top one. And if it drops, so this one has got a fully filled subshell. So if this electron configuration is lower than you expect, then the ionization potential is actually smaller. And so again, it confirms the same conclusion that the unusually high ones did. That if you have a stable, fully filled subshell or half-filled subshell, then you have these trends in the ionization energies. let's redo this one, but let's do it for oxygen. I'm kind of running out of space. Let me go ahead and erase it. Much better than a pencil because it's perfect. Okay, so now let's look at oxygen. So we have oxygen here, 1s2, 2s2, 2p4. An oxygen cation, 1s2, 2s2, 2p3. And that's a half-filled p subshell. And so it looks like the cation might be stabilized. And so if this energy level is lower than what we expect because of this half-filled subshell, then the ionization potential is unusually low. And that's what we have for oxygen. So those are all of the 5 trends that you can pull out of this ionization data. And it also is really good for practice for electron configurations. So this is the data where we get these claims that half-filled subshells are stable, fully filled subshells are stable. The next electron beyond a half-filled is easy to ionize, and the next electron. And so that's going to make oxygen more reactive than nitrogen. It's going to make sodium more reactive than neon. And so there's going to be a lot of chemical trends that come out of this. Yes?
So based off of this graph, does that mean xenon is more reactive than oxygen?
No.
Just because if you look at the energy levels, they're
Yeah.
lower.
Well, not quite oxygen, but it's certainly lower than, say, fluorine, you know. That's a good question.
Isn't it because of like the size and like how far out the shells are?
Yeah, I mean, what's interesting about it is there are xenon compounds. You can oxidize xenon, but there really aren't any known of neon, you know. So, and this is the first ionization potential. So it's talking about things that would require removal of electrons from these particular atoms.
Okay.
You can react xenon with fluorine, which is really weird because fluorine's higher in terms of its ionization potential. But that also means it's harder to pull electrons from fluorine, but it may be much easier to donate them. So electron affinity. And so that's a part of the data that's not shown here. So, yeah. But that's a good question and good insight to look at this and say, what does this mean in terms of relative reactivity?
Mm-hmm.
For things that require oxidation of these, which is a removal of an electron, then this would be a good chart to use.
Okay.
Yeah.
So not necessarily just general reactivity.
Right, but
Okay.
reactivity with oxidation. If these were to be oxidized in a reaction, this should be related to the relative
Okay.
reactivity.
That makes sense.
Okay, good. Yeah, because it's really easy to oxidize all the alkali metals and difficult to oxidize the noble gases. And we do see that the larger noble gases are easier to oxidize than helium and neon.
Mm-hmm.
Yeah, excellent. Let's play a Kahoot and see if we got the trends. Okay, 7315239. 7315239. And the trends are pretty easy. You probably have those in mind, but you got to pay attention to the words like shell versus subshell and those kinds of things. I know it's kind of a smaller group today. And they got the Halloween pumpkin and the ghost. That's nice. Yeah. Anybody else? Speak up? Okay, let's go. So give a basic reason for the low first ionization energy for rubidium. And so the red is fully filled, valence subshells are stable. Blue is half-filled, valence subshells are stable. The orange is half-filled, valence shells, are stable, and then the green is fully filled valence shells are stable. So all of them are valence. So you're really just looking at between subshells or shells. Okay, kind of a big spread. Now, what we're talking about rubidium, we fully filled a whole shell like krypton, and that stabilizes the cation. And so then rubidium is one past that. So it's a fully filled valence shell in that case. Okay, what about gallium? Give a basic reason for the low first ionization potential of gallium. It's one after zinc. Okay, so either fully filled subshells, which is red, half-filled subshell, which is blue, half-filled valence shell is orange or yellow, and then fully filled shell is green. Okay, it's red because you're one past a filled subshell. So the D10 is zinc. We've filled up that D set of orbitals, and the very next one is one past it. So the cation is stabilized, which means it's a low ionization energy. I could ask all these same questions but just stabilize the cation or the neutral. Okay. Give a reason for the high first ionization potential for magnesium. So magnesium, we go sodium, magnesium, aluminum. So magnesium is a little higher. So is it fully filled subshells, half-filled subshells, half-filled shells, or fully filled shells? Okay, so still a majority. It's the fully filled subshell because it's the, which one is it? Second, no, the magnesium's third row, so that's the 3s2, okay, for the neutral. And then the cation would be 3s1. So the neutral is stabilized, makes it a high potential to ionize it. Okay. Okay, now for nitrogen, it's got a high first ionization energy. Is this due to a fully filled subshell or a half-filled subshell, a fully filled shell or a fully filled or a half-filled shell? Okay, this is the half-filled subshell. It's P3. Notice all of those under nitrogen would be P3 systems. So this is a new vocabulary word. I'm not worried about 2P, 3P, 4P. They all have a P3 under nitrogen. And so they'll have the same term symbols even. So nitrogen and phosphorus and arsenic, they will have the same term symbols. They'll have the same angular momentum quantum numbers, the same spin states, and so on, because they're all P3 systems. And so when we talk about a P3 system or a D5 system, whatever, you're just focusing on that subshell. And then lastly, give the reason for the low first ionization energy for oxygen. Very good. So it's the same reason, right? In nitrogen, the neutral was stabilized. It was hard to ionize. In oxygen, the cation is stabilized, and it's easy to ionize. So you're just looking to see which one is stabilized, the neutral or the cation. And you know that because of the electron configurations. So let's revisit chromium now. So chromium's electron configuration, if you look at it here, it's D4. But that atom can be more stable if it gets to a half-filled subshell. And so it'll steal one from the 4s, which is also half-filled. And so let's think about what's going on in chromium. Why are all these half-filled subshells stable? Well, that electron in the 4s, it's the 4s, right? Yeah, the 4s has its own independent view of the nucleus. It doesn't have another electron in its orbit. And then how many orbitals are there in the D subshell? There are 5 of them. And so if I have 1 electron in each of those 5, each electron has its own view of the nucleus. And it's not sharing that view with anybody else. So it makes sense that these half-filled subshells are really stable, meaning they're lower in energy. Once you have, and it also means that there's no break in the symmetry. If I have 4 electrons in the D shell, yeah, they all have their own independent view of the nucleus. But once I get that 5th, there's that electron cloud. It's almost like a resonance effect. Once they're all the same and have 1 electron in each, the atom is more stable. Just like the noble gas. Once you get 2 electrons in every orbital, the cloud is perfect then. Okay? And that perfection seems to be stable than imperfection. So a half-filled subshell seems to be more perfect than something close by. And so you have these independent views of the nucleus by each electron in each one of those independent orbitals. Okay. So I think that's everything I wanted to say about electron configuration. Practice, practice, practice. So go through, this should be able to, now the F block is really screwy. And so, yeah, you can try to look those up. They're interesting, but the trends really start to get broken in the F block. So we're really focusing on the top 2 rows of the D block and above. Okay. Yeah, it breaks off and it doesn't, like you get a D electron and then an F electron, and so it's really weird.
Yeah, I was looking at the graph.
And you can find periodic tables online with all the electron configurations on them, so you can check your work. And there may even be one in the book.